Hello my friends and welcome back to the You Can Do TV channel. Track the Appomattox oil platform navigating storm-threatened waters under controlled tow. This offshore production platform weighs more than an aircraft carrier and travels as a fully assembled topside and hull unit. Fabrication integrates reinforced steel modules, living quarters, drilling systems, and processing equipment into a single offshore structure. Hull framing distributes stress loads across multiple support nodes during tow operations. Heavy lift transport vessels secure the platform using multi-point fastening systems and ballast control. Ocean transit planning calculates route deviation, tow speed, and wave tolerance thresholds. Ballast adjustments regulate draft and stability throughout changing sea states. Weather routing teams analyze storm trajectories and pressure systems in real time. Then a super typhoon shifts course. Wow, that escalation raises the stakes instantly. Structural endurance becomes critical as wind force and swell height increase. The platform's center of gravity and load distribution determine motion response under extreme conditions. Finite element analysis models structural response to high wind and wave impact. Tow vessels maintain controlled alignment to prevent lateral drift. Steel mass and reinforced bracing counter torsional stress across deck levels. Seriously, moving something heavier than a carrier through open ocean sounds unreal. After clearing the storm path, transit resumes under monitored conditions toward offshore deployment waters. Mooring integration and subsea connection planning follow arrival. The Appomattox platform represents large-scale offshore energy infrastructure engineered for transport resilience and operational durability. This vessel can lift an entire offshore platform in one single move. Deck crews position incoming pipe joints along the firing line, locking each section into place for alignment. Each joint is measured and beveled to match welding specifications exactly. Automated welding stations travel around the pipe circumference, depositing consistent weld passes layer by layer. Multiple welding heads operate in sequence to maintain production continuity. Sparks flare briefly, then the seam settles into a solid bond. Whoa, that connection looks unstoppable. After welding, non-destructive testing units scan every seam. Ultrasonic inspection verifies internal weld integrity across the full wall thickness. Any irregularity triggers immediate correction before the pipe advances. Tensioners grip the coated pipe and guide it toward the stern ramp. High-capacity tension systems control pipe curvature during offshore deployment. Out there, the line arcs downward into open water, steady and controlled. On board, massive cranes handle topside modules destined for offshore platforms. Heavy lift beams distribute load evenly across lifting points. Operators coordinate through integrated control systems, linking deck equipment and bridge commands. Dynamic positioning thrusters counteract wave and wind forces to maintain vessel stability. The scale hits you all at once. Seriously, that lift is enormous. Below deck, power generation units supply continuous energy to welding arrays, tensioners, and thrusters. Redundant engine configurations secure uninterrupted offshore operation. Cable management systems route electrical supply safely across working zones. Central monitoring stations track mechanical performance in real time. During platform removal campaigns, lifting arms secure entire topsides in a single hoist. Structural supports absorb load transfer during separation from jacket foundations. The structure rises cleanly from its offshore base. What a sight! Pipe after pipe extends across the seabed, forming subsea transport networks for energy delivery. Coating systems protect each pipeline segment against corrosion in marine environments. Heavy pipelay vessels and lift systems operate as coordinated offshore production units, turning engineered steel into installed infrastructure beneath open water. Five ZPM CULCS cranes now handle 18,000 TEU container ships at full height and outreach. After a 2-month ocean transit, the transport vessel positions near the terminal berth. Tug assistance stabilizes alignment alongside the quay. Once moored, preparation crews inspect locking points and lifting interfaces. This scale right here changes the skyline in one move. Dot. Heavy lifting operations commence using onboard lifting systems integrated into the transport configuration. Load transfer calculations determine the sequence for safe quay placement. One crane at a time is raised, rotated, and lowered onto pre-installed rail tracks. Rail gauge alignment is verified before final seating to ensure gantry travel accuracy. The clearance between wheels and track edges is checked across the full span. That first touchdown on the rails feels huge. Each ULCS crane features a hoist height reaching approximately 50 meters above quay level. The extended hoist range allows vertical access across ultra-large container ship stacks. Earlier generations operated around 30 meters, marking a substantial increase in operational envelope. The boom outreach spans across the beam of the largest container vessels currently in service. High-capacity trolley systems support efficient container transfer cycles. Electrical integration follows mechanical positioning. After calibration runs along the quay, the cranes stand prepared for container operations at full outreach and lifting capacity. Crane work is often mistaken for simple vertical lifting without complex load planning. Each lift requires predefined load calculations based on weight, radius, and boom configuration. Highway construction zones set the stage for complex crane deployment. Outriggers extend outward on the Leibher LTM 11200NX, transferring load into the ground through reinforced pads. Outrigger beams lock mechanically once fully extended to secure structural support. Ground pressure calculations determine outrigger spread and support configuration. The telescopic boom rises section by section, locking hydraulically into position. Telescopic sections extend in sequence under controlled hydraulic pressure. That boom height shifts the entire scale of the job in seconds. During bridge component placement, rigging crews attach slings to pre-marked lifting points. Rigging hardware is rated according to calculated working load limits. Load charts guide boom angle and counterweight selection for each lift scenario. The crane rotates smoothly, aligning structural segments over their target positions. No rush here, just deliberate motion under full capacity. On another site, the Hitachi Sumitomo SCX 2000 crawler crane assembles with lattice boom sections pinned together at ground level. Lattice pins are secured with retaining mechanisms to prevent axial movement. Crawler tracks distribute weight across soft terrain to maintain stability. Once erected, the lattice structure provides extended reach for steel girder installation. Seeing that lattice stretch across the skyline changes perspective instantly. The Tadano AR5500M handles heavy components requiring high lifting capacity within limited setup space. Counterweight modules are installed in sequence to balance rated load. Counterweight mass is configured according to lift radius and structural demand. Hydraulic systems manage hoist speed and boom articulation through centralized operator controls. One smooth lift and the structure settles exactly where planned. Urban operations introduced the Tadano ATF300G6, configured for maneuverability and rapid deployment. Multi-axle steering supports tight access routes common in city projects. Steering modes include coordinated axle movement for reduced turning radius. Outriggers deploy, the boom extends, and prefabricated sections are placed with controlled descent. That placement lands clean. Drone aerial footage captures each mission from above, documenting crane positioning, lift geometry, and coordinated site movement. Aerial perspective assists in evaluating spatial clearance and swing radius. Swing radius calculations account for counterweight rotation and boom length simultaneously. Across multiple projects, these crane systems execute highway and structural lifts through calculated setup, calibrated load management, and controlled hoisting sequences. The stability of 435 megawatts turbines relies entirely on earthwork. Bulldozers strip surface vegetation and unsuitable soil layers to reach stable ground. Geotechnical surveys determine bearing capacity prior to excavation depth approval. Excavators then remove large volumes of soil across the dam footprint, shaping the foundation profile according to engineering drawings. Compactors pass repeatedly over each layer to increase soil density. Field density tests verify compaction results against design standards. Honestly, that level of ground control sets the entire future structure. Embankment zones rise gradually using selected fill material transported by dump trucks. Each layer spreads evenly. Then compaction equipment reinforces stability. Moisture conditioning maintains optimal compaction performance within specified ranges. Diversion channels manage river flow during foundation work, preventing water intrusion into excavation areas. Seeing the scale of coordination here feels intense. Slope protection measures follow grading operations to reduce erosion risk. By the time structural works proceed, the prepared base supports the load requirements of all 4 generating units. How do you reposition a 4 500-ton TBM Martina underground using AIR MOVER 3000? That number alone resets expectations for heavy equipment handling. The cutter head diameter measures 15.15 meters, forming the front mass that had to rotate as one integrated body. Total allowed load capacity for the shifting system reaches 200 tons. Preparation required positioning a complete TBM cradle set, composed of 10 individual cradles, arranged across a 10 by 12.5 meter platform. Each cradle connected to compressed air cushions, 80 units in total. Every single air cushion supports up to 43.5 tons. The backup wagon alone contributes 550 tons to the overall configuration. The cradle grid distributes structural loads across the full support footprint. That is not something you casually spin around. Instead of dismantling the machine, crews configured the air cushion-based carrier system beneath the TBM structure. Compressed air feeds into reinforced membranes, creating a thin lifting layer between steel and ground. The hovercraft principle reduces friction to a minimal sliding resistance. Air pressure levels remain balanced across all 80 cushions during lift. Once pressure stabilizes, the machine rises slightly, distributing weight evenly across the cushion grid. Rotation did not rely on brute mechanical torque. Controlled lateral force applied gradually shifts orientation. Hydraulic push units guide directional movement while monitoring alignment references along the tunnel floor. Load sensors track real-time weight distribution across all cushions during displacement. Alignment references are fixed along the tunnel invert to verify angular progression. That level of coordination feels intense. The 180-degree rotation unfolds step by step. Incremental angular adjustments ensure the cutter head clears structural boundaries. Air pressure levels adjust continuously to maintain uniform lift. Centralized control synchronizes air supply, hydraulic thrust, and positional feedback. Angular deviation is measured continuously throughout the rotation cycle. No rush movements, no sudden corrections, only measured repositioning across the prepared base. During lateral translation, the TBM glides over the cushion array, shifting its axis until alignment matches the outbound tunnel direction. Backup systems remain attached, moving together as a unified mass. The entire 4,500-ton assembly moves without mechanical wheel contact. Seriously, shifting thousands of tons like that challenges common sense. Completion arrives once the cutter head faces the new excavation path. The cushions gradually deflate, transferring weight back onto structural supports. Final verification checks confirm angular accuracy and structural integrity before excavation resumes. AIRM OVER 3000 proves that controlled air pressure can reposition one of the heaviest tunnel boring machines ever rotated underground, achieving a record TBM equipment shifting time of 15 days without dismantling TBM Martina. One calibrated spray bar covers an entire lane in a single sweep. Traffic is cleared, and the pavement surface is cleaned to remove dust and loose debris. A clean base allows uniform asphalt contact across the entire lane width. The asphalt distributor moves forward at a controlled speed, spraying a calibrated layer of liquid asphalt binder across the road. Spray bars maintain consistent application rates from edge to edge. The binder forms a continuous film that prepares the surface for aggregate bonding. Right behind it, the chip spreader releases a measured layer of crushed stone. Aggregate size is selected according to roadway load requirements. The spreader gates adjust to deliver even coverage across the full width in one pass. Wow, that blanket of stone drops fast. Dot. Pneumatic tire rollers follow immediately, pressing chips into the asphalt layer. Rolling embeds the aggregate into the binder to achieve mechanical interlock. Multiple passes increase chip retention and reduce loose material. Steel drum rollers may continue compaction to seat the surface fully. Proper compaction improves long-term surface durability. Dot. After rolling, excess stone is swept away to clear the driving path. Brooming removes unattached aggregate without disturbing embedded chips. The surface is then opened to controlled traffic, allowing natural seating under vehicle loads. That first drive across fresh chip seal feels different. Dot. Full-width chip seal creates a protective wearing course that seals cracks, restores skid resistance, and extends pavement service life using coordinated distributor trucks, chip spreaders, and rolling equipment. Dot.
A 250-ton giant called CC6800 doesn't just stand there. It moves earth-shaking loads with total confidence. The Mammoet Terex, DeMag, CC6800 unit #1800, complete with a 66-meter main boom and an 84-meter luffer, is being assembled right at the K+S Potash Canada site in 2015. Once the base is secured, the lattice boom system is pieced together. Inserts slide, pins lock, hydraulics engage. This huge crawler crane is ready for heavy lifting. Meanwhile, the assist crane, a Kobelco CKE2500 unit #1423, works alongside to position counterweights and support components. Seeing those massive steel sections lifted into place kind of hits you. With dual redundant engines, a robust quadro-drive undercarriage, and the flexibility of modular boom and superlift configurations, the CC6800 is engineered for maximum power and stability. It can reconfigure for different jobs, switch between boom/jib setups, and adjust counterweights to match load demands. Feels like watching controlled power tuned for extremes. At the end of assembly, the site stands ready. The CC6800 and its helper, CKE2500 together, transformed raw steel and hydraulics into a crane capable of tackling the toughest lifts on that potash project. Hard to get over how relatively smooth everything looks, even with such massive parts in play.
Steel hulls regain strength as M/TC Victory enters Odessa shipyard in Varna for scheduled repair work. Dock teams secure the tanker, inspect structural zones, and prepare surfaces for correction. Components are serviced and aligned to restore operational reliability. That scale still feels serious, even alongside the dock. Tanamera Ship Management returns after decades for a reason, under proven methods. Compact lifting changes the way work gets done when the microcrane's M1 portable mini crane enters tight job sites. Designed for controlled handling rather than raw size, the M1 moves through doorways and elevators before any load is even attached. Battery power drives hydraulic boom movement, while operators position the base exactly where space is limited. That narrow footprint solves problems long before lifting begins. Outrigger legs swing out to stabilize the crane, and the counterweight rack slides back to create a solid working stance. Once set, the electric winch handles cable lengths up to 160 feet, allowing vertical work across multiple floors. Loads are picked, carried, and repositioned without constant resets. This pick-and-carry ability cuts wasted motion on crowded sites. Steering allows tight turns, and spring-loaded casters keep balance as weight shifts. Rated for 1 ton, the M1 handles HVAC units, glass panels, pumps, and structural components while staying compact. Seeing heavy parts move through a hallway still feels unreal. Safety systems meet major standards, keeping lifts predictable instead of rushed. When tasks finish, the crane breaks down for transport by truck bed, elevator, or stairwell. That flexibility explains why crews rely on it again and again. Installation crews and the SANY SCC 6500A crawler crane build a wind-ready lifting platform. Preparation focuses on aligning the upper and lower structures so later movements stay predictable. Assembly vehicles assist with positioning while crews install slewing bearing pins that will carry rotation under extreme loads. Correct pin seating at this stage defines how evenly rotational forces are distributed later. This early alignment quietly controls how confident every later swing will feel. Attention moves to the luffing system. The luffing mast is installed and raised beyond 95 degrees, then brought back into a working range that supports heavy lifting efficiency. That angle selection protects load charts instead of chasing maximum reach. Choosing this angle protects lifting capacity instead of chasing height. Track frames are lifted next, hydraulic locking pins engage, and hoses are connected to restore drive and steering functions. As the undercarriage outriggers retract, the crane transitions onto its crawler tracks, gaining full ground contact and stability. Once the crane settles onto its tracks, ground pressure becomes evenly shared across the system. The superlift configuration follows. Central trays, walkways, and counterweight platforms are installed to prepare for long-radius work. Rear counterweight trays and blocks are added to balance the system as reach increases. Superlift mast boom sections are assembled on the ground, secured with hydraulic pins, and lifted into position on the main machine. Seeing those sections align without correction feels like a rare, smooth chapter in heavy assembly. Once raised, tie bars connect the superlift mast to the main boom system, creating a shared load path that reduces stress during lifts. Main boom installation comes next. Boom sections are connected sequentially, electrical cables and plugs are routed, and reeving is completed to support lifting operations. Cable routing choices at this stage prevent interference during complex boom movements. The crane now carries its recognizable working profile. This is where the machine stops looking temporary and starts reading like a purpose-built tool. Lifting geometry is adjusted to the optimal 65 to 75 degree range, balancing reach and control for wind turbine components. Throughout the installation, sequence outweighs force. 5 installers complete the assembly in approximately 16 hours by following strict order rather than pushing speed. It's surprising how controlled the pace stays for a crane designed to handle this scale. Each pin, hose, and counterweight locks in performance well before the first turbine section arrives. By the time installation concludes, the SCC 6500A stands fully configured for wind lifting operations. Structural balance, mechanical geometry, and operational readiness are already decided. What happens during lifting depends entirely on this groundwork, and there is no recovery for shortcuts taken here. The crane does not prove itself during the lift, it proves itself during assembly. Few vessels test a port's limits like the OOCL Hong Kong as it arrives for its maiden call at the port of Felixstowe. The container ship enters service with a carrying capacity of 21,413 TEU, setting a new benchmark for global shipping routes. That scale alone changes how terminals plan every single move. Stretching 399.87 meters long and 58.8 meters wide, the ship's dimensions demand precise berth alignment and coordinated harbor operations. Its maximum draft of 16 meters requires strict tidal windows, while the 210-890 gross tonnage pushes infrastructure to operate at full capability. You can feel how little margin there is when a vessel fills the horizon like this. Built at Samsung Heavy Industries in Jeoje, South Korea, the ship sails the Asia-Europe trade lane under OOCL's LL1 service. Designed for 23 knots, it represents the return of OOCL to the UK's largest container port after 17 years. That comeback carries real weight for global logistics. How does a transfer car system move Indiana SSN 789 from the build hall to launch at Newport News Shipbuilding? Rather than staying hidden in a hull, the vessel shifts onto a transfer car system that carries the full hull weight with steady control. That first roll already decides whether the launch stays calm or turns tense. As the submarine advances, alignment checks guide every meter of travel toward the floating dry dock. Loads are balanced continuously to keep the hull level and stable. One clean line here saves hours of correction later. Once positioned, the dry dock takes over, allowing the structure to float free while support systems disengage. The dock is gradually flooded, lifting Indiana SSN 789 from its cradles. Seeing steel start to float still feels unreal. The submarine enters the James River, marking the transition from construction to operational testing. That quiet slide into water carries years of work in a single moment. Coordination outweighs sheer lifting power during the installation of 4 121-ton electrical transformers by Advantis projects. Long before cranes engage, multi-axle trailers position each transformer with routing planned down to the meter. Transport accuracy here prevents stress before the lift even exists. Once on site, the focus shifts to placement rather than speed. Heavy lift cranes handle vertical movement, while jacking and skidding systems guide each unit horizontally onto prepared foundations. That sideways control matters more than raw height. Load paths stay predictable, keeping forces balanced as steel meets concrete. One slow adjustment can reset the entire alignment. As transformers settle, accessories follow in a defined sequence, locking the system into its final configuration. This stage decides whether maintenance later stays simple or turns painful. Crews stay synced through timing, not signals, as each move depends on the one before it. It's wild how quiet a site gets when everyone knows the next step. With all 4 units seated, checks confirm elevation, spacing, and interface points. The work looks complete, yet the real success sits unseen beneath the housings. Getting heavy equipment onto foundations without drama is the real win. What powers up later depends on that calm precision today. Stay through this breakdown to understand how crude oil is separated, upgraded in ISO CRACKING reactors, and finalized into certified premium base oils. Crude oil moves through distillation columns, separating VGO and Dow streams before raffinate enters the ISO CRACKING reactor. Heavy molecules are restructured into higher performance components, then waxy lube oils are refined into consistent base stocks. Millions of tons of limestone move each year under Responsible Issue 3.0 controls, guided by BES 6 environmental standards. Extraction zones are mapped through staged planning, then blasting, hauling, and stockpiling follow regulated layouts tied to land rehabilitation targets. High output doesn't cancel accountability. That's structure layered onto scale. Production advances while safeguards hold firm. Many assume blasting dominates brown coal mining, yet RK5000 performs continuous overburden removal instead. This last machine of its type handles overburden removal on a scale few systems attempt. Steel structures stretch outward while the rotating wheel cuts through layered soil, feeding conveyors that transport waste away. Continuous excavation replaces blasting cycles, and that shift keeps production steady. Track assemblies reposition the body along the pit edge, allowing the boom to maintain consistent cutting depth. That wheel doesn't nibble at the earth. It commits fully. Material flows across linked belt systems, separating topsoil and sublayers until coal seams appear. Operators regulate wheel speed, conveyor load, and travel alignment from an elevated cabin overlooking the cut. Coordination here decides output, not brute force alone. Brown coal then transfers to downstream handling units for further movement. One look at the full boom span. Wow, that reach stretches beyond expectation. No sudden pauses, no explosive resets. Excavation advances in a controlled, ongoing sequence. The RK5000 stands as a mechanical heavyweight, built for endurance and sustained surface mining depth. Frac Blender Unit delivers 140 barrels per minute while integrating Cat C18 engines, Namco gearbox control, and synchronized proppant feeding in one continuous system. Dual Cat C18 Tier 4 final engines deliver 1,600 total horsepower, driving the Namco gearbox through a hydraulic clutch for controlled torque transfer. Power delivery here isn't just muscle, it's managed force. Proppant enters a 71-foot hopper and feeds into 3 augers capable of moving up to 21,000 pounds per minute. Those augers regulate sand flow into the tub, maintaining blend consistency before fluid integration. That's where uniform slurry quality is decided. 2 Acrison dry feeders meter additives with measured accuracy, while 8 Waukesha chemical pumps inject liquid components directly into the mixing stream. Oh, that integration hits hard. Everything converges in seconds. The mixing tub circulates materials under calibrated speed control, preventing separation while sustaining high-volume throughput. Operators monitor load balance, engine output, and feed rates from centralized controls, adjusting parameters to match formation demands. Stable blending reduces downtime and protects downstream pumps. Torque flows from engines to gearbox, from gearbox to augers, and finally into the blend circuit, forming a closed operational chain. No unnecessary handoffs, no lag between components. Each subsystem supports the next in real time. System continuity keeps frac schedules on track. With proven 140 BPM capacity, triple auger proppant delivery, and integrated chemical management, the frac blender unit converts raw inputs into pump-ready slurry under sustained field conditions. That level of coordinated output, wow, that's production confidence. A dedicated dragline like the Liebherr 81 OOHS rarely appears in small pits, yet here it dominates dry gravel mining. Liebherr 81 OOHS dragline crane operates in dry mining conditions in Iowa, working a gravel pit with a 5-yard bucket that reaches deep and pulls material in long, controlled arcs. The machine positions along the edge of the cut, lowering its bucket through cables stretched across the boom, then dragging through compacted aggregate to fill each load. That bucket bite is deeper than it looks from a distance. Once filled, the dragline swings smoothly toward the spoil area and releases the gravel in a broad spread, building stockpiles layer by layer. This is where raw ground turns into real volume in a hurry. Repositioning happens gradually to maintain reach and balance, allowing continuous excavation without tracked travel every few minutes. The extended boom provides working range that reduces unnecessary movement across the pit floor. You wouldn't guess a machine this size could move with such control. Load after load, the Liebherr 81 OOHS keeps carving, pulling, and casting, proving why dragline systems remain relevant for large-scale dry mining operations. An 800-meter horizontal directional drill drives a 48-inch subsea pipeline bore through solid granite using controlled steering and staged reaming. A new offshore oil development required a shore connection capable of handling continuous crude transport. The solution relied on horizontal directional drilling to pass beneath solid rock instead of disturbing the coastline. The bore would exit far below sea level, which meant hydrostatic pressure and geological resistance had to be calculated in advance. At that depth, alignment tolerance isn't optional, it's structural survival. The operation advances first with a steered pilot drill fitted with a 10-5/8-inch tricone bit. Rather than forcing size immediately, the pilot hole establishes the exact trajectory across 800 meters of dense granite. The pilot path defines the center line that every enlargement stage must follow. Steering adjustments are made incrementally to maintain line and grade. The bottom hole assembly is replaced frequently to protect tool integrity under heavy torque and abrasive contact. Granite at this hardness level accelerates cutter wear and increases rotational load. Directional accuracy here determines whether the reamers can even follow. That dependency raises the technical stakes fast. After confirming pilot alignment, forward reaming enlarges the bore in 3 controlled stages: 28 inches, 38 inches, and finally 48 inches. Each pass widens the tunnel while preserving curvature limits. Each diameter increase multiplies the contact surface between tooling and rock. During the 38-inch phase, a large hole opener fractures and removes massive volumes of granite. Miles of drill pipe are tripped in and out repeatedly, extending and retracting the string as diameter increases. Pipe handling at this scale becomes a project within the project. One miscalculation in sequencing would slow everything down. Seawater circulates continuously through the bore to flush cuttings back to the entry side. The fluid transports crushed granite fragments while stabilizing pressure inside the tunnel. Fluid return flow provides a visible indicator of bore cleanliness and circulation continuity. Without consistent circulation, debris accumulation could restrict movement or damage tooling. Granite fractures unpredictably under load. Wow, that resistance underground doesn't negotiate. Drilling operations run 24 hours a day across 2 shifts to maintain momentum. Crews rotate while the drilling system remains active. Downhole tooling undergoes constant inspection and maintenance before each advance. Connections, cutters, and stabilizers are checked to prevent mechanical failure at depth. Sustained 2-shift rotation keeps drilling parameters consistent across the entire bore length. Reliability below the surface directly controls surface progress. Nobody wants a retrieval scenario from hundreds of meters under rock and sea. Following the final 48-inch reaming stage, the completed bore receives internal quality verification. The tunnel diameter and wall condition are assessed to confirm readiness for pipeline installation. That validation ensures structural stability before product transport begins. It demonstrates how controlled engineering and staged enlargement can drive a 48-inch tunnel through granite far below sea level without compromising safety or alignment. And carving that diameter through solid rock at that depth, yeah, that's serious drilling discipline. Blade control shapes the final result, and Moto-Niveladora New Holland RG140B completes slag finishing with steady articulation and measured hydraulic input. Operator Danilo lowers the moldboard gradually, aligning it to skim high ridges left from earlier spreading. Instead of cutting deep, he maintains a shallow angle to redistribute material across the surface. Small steering inputs keep the front axle aligned while the rear tandem grips the compacted layer. Hydraulic tilt adjustments refine cross slope as the grader advances at controlled speed. Slag reacts in loose granular waves before compacting under the rear wheels. Danilo feathers the blade along the boundary during the final pass, trimming excess buildup. Clean edge finishing defines the line before compaction equipment follows. Moto-Niveladora New Holland RG140B exits the stretch, leaving a leveled, prepared surface ready for the next phase. Controlled blasting turns stored chemical energy into directed rock fragmentation through a measured ignition sequence. Preparation moves from material staging to borehole layout across the blast pattern. Technicians position drilling equipment to create evenly spaced holes based on burden and spacing calculations. Hole depth and diameter follow the rock profile and target fragmentation size. Final safety checks confirm circuit continuity and clearance of personnel from the blast zone. Upon initiation, the detonation wave travels through the explosive column, generating high-pressure gases that fracture and heave the rock. Post-blast inspection evaluates fragmentation size, muck pile distribution, and wall condition. Adjustments to burden, spacing, or charge weight are planned for the next round based on measured results. Dry, non-destructive excavation changes how underground surfaces are exposed without tearing up the ground. Vacuum excavation units operate using high-powered airflow to dislodge and extract soil while protecting buried utilities. Air vacuum systems lift loose material through reinforced hoses into sealed debris tanks. Controlled suction reduces the risk of striking live cables or pipelines. Instead of mechanical digging, soil is displaced by airflow and extracted vertically. That difference alone can prevent expensive damage. For tougher ground conditions, additional units apply water pressure ranging from 3,000 psi up to 15,000 psi to break compacted layers. The loosened material is immediately removed through the vacuum system, limiting surface disruption. High-pressure water paired with extraction allows targeted exposure without trench overcut. Oh wow, that pressure range covers everything from soft clay to stubborn fill. These units support infrastructure access across dense urban environments. Maintaining underground asset integrity directly supports public safety and service continuity. Equipment configurations vary depending on site depth and soil classification, yet the operating principle remains consistent: loosen, extract, contain, and transport spoil securely. That straightforward sequence keeps excavation controlled and predictable. A single hoe trapper carries 8 500 vehicles in one voyage. Designed as a New Horizon vessel, this ship expands cargo flexibility through structural and ramp engineering. Hull fabrication establishes a 199.9-meter length and 36.5-meter beam within post-Panamax limits. Steel block sections align, weld, and integrate into a reinforced two-pillar structure that distributes deck loads efficiently. Fourteen decks stack vertically inside the carrier, with 5 hoistable platforms adjusting clearance for mixed cargo profiles. Hoistable decks modify vertical spacing to match cargo height requirements. Internal ramps connect deck levels, and all are movable to optimize cargo routing. Movable ramp systems increase usable lane meters across configurations. A stern ramp enables roll-on and roll-off operations for heavy and oversized freight. Capacity planning targets 8 500 CEU supported by deck areas ranging from 71 to 400 square meters. Deck strength ratings correspond to axle load specifications for rolling cargo. Extended roll trailer systems allow transport of trams measuring up to 43.5 meters in length. That length stretches across multiple deck zones, creating a coordinated loading sequence. Seriously, a tram inside a ship feels unreal. Latest information technology integrates navigation data, cargo monitoring, and voyage optimization tools. Digital load management systems track weight distribution across all decks. Equipment upgrades support wider cargo categories beyond passenger vehicles. Structural layout, adjustable decks, ramp mobility, and reinforced framing collectively expand operational range. Oh wow, that internal space just keeps going. The hoe trapper embodies large-scale maritime engineering configured for high-volume, high-diversity transport. How would cargo flow change if every container move relied on automation? Cargo vessels berth along reinforced quays equipped with ship-to-shore gantry cranes. Each crane locks onto a container using a spreader frame and lifts it vertically onto automated transport units. Laser positioning systems guide crane alignment over container rows. Automated guided vehicles receive containers and travel along programmed routes across the yard. Embedded navigation markers coordinate direction and speed without onboard drivers. Central control software assigns transport paths based on stacking density and vessel schedule. Containers transfer toward stacking zones arranged in high-density blocks. Wow, that coordination feels unreal. Automated stacking cranes operate within each yard block, lifting containers and placing them into assigned slots. Sensors confirm container identity and placement accuracy through digital verification. Real-time inventory tracking updates location data after every lift cycle. Yard layout algorithms optimize stacking height and retrieval order according to outbound demand. Truck lanes operate at the perimeter through automated gates. Drivers scan identification codes while gate systems validate cargo release data. Optical character recognition captures container numbers at entry points. Once cleared, stacking cranes retrieve designated units and position them onto chassis units. Vessel loading follows a synchronized sequence. Transport units deliver outbound containers beneath quay cranes, which lower them into assigned ship bays. Load planners calculate weight distribution across deck and hold positions to maintain vessel stability. Seriously, thousands of containers move like pieces on a digital board. Data integration links berth scheduling, yard allocation, and gate operations into one coordinated system. The Container Terminal Rotterdam represents high-capacity maritime logistics structured around automation, throughput efficiency, and continuous cargo visibility.